Yeah.
Okay, thank you for the nice introduction. Yeah, time flies. It's been already 10 years anyway. So yeah, let's talk, present some recent work on multi-stage reasoning for video understanding and scene generation. So two completely different domains. Let's not switching to slides. Okay, so basically, as Anup already mentioned, so what we want to do, we have an agent, can be an LLM or something else, and we want to A, use tools, and then B, I won't talk about this today, but it's also interesting to have approaches which use memory. So basically, those two things can really augment the agent and give them additional information. And so basically the tools, what can they do? They can have additional information, call, for example, detections, temporal and spatial temporal detections in video, or some other placements in 3D scene generation. And then memory can help you to understand fine-grained and rare classes and become more efficient. So the two presentations today are first, we'll talk about video question answering with reasoning. So basically what we want to do, if we want to understand the video, we can, the cat misses the target above the closet and fails. We need to detect what is going on when the cat fails and what is happening next. And so basically, videos go beyond static images. They want to capture the temporal causal relationships, and they're long and they can't process every frame. And so basically here you see that the clip is quite short, but basically now we have hours of video, and at some point they cannot be processed in one go by a black box LLM method. And so here, for example, what these LLM methods do, they kind of take of input the video and the question, and then they give us output what's happening. The cat misses the target above the closet and falls. And so basically these methods are efficient, but challenging to interpret. So basically if something goes wrong, you don't know why, and you have to start off from scratch or do something else. And so here there are different approaches. And one was to use code generation to generate a plan or program. And then this plan or program can be executed and give the response. And then here you can see basically it's a single stage approach. And then basically the second approach here is we want to have something which is more modular and is closer to reasoning. So this is also somewhat connected to all these reasoning traces, and you can think of basically the LM wants to generate the different stages, and then you want to see what are the agents you're calling. And if it's modular, basically it's not as static as a program. And so here what we did, we first had a simple baseline, and the baseline GCEF, it first captions the video, every frame, and then these captioned frames are taking this input together with the question and outcomes and answer. But this is a good baseline. I saw a paper yesterday who do something similar for reasoning traces. You can use this baseline to really see how well it performs. And actually it was surprisingly efficient and outperformed models like these program generators, which are WiperGPT. And then so our approach, what we did is we had this multi-stage reasoning. The first stage is event parsing. So we take as input the question and see what's relevant in the question. Then we call some grounding modules. So this is something which is important, that basically we localize in more detail the information in the video in space and time. And then we have a reasoning LLM, which takes as input the objects, it captions them and generates the caption and then predicts the answer. And between all these stages, we have a shared memory which can see what has been extracted so far. And so if you zoom into the different stages, the event parsing focuses on the language. It instances the events and relations, and then parses what is actually relevant to the API. For example, we can say, if it's at the end of the video, we know that we have to look at the last part of the video. If it looks for a cat, we have to localize the cat. So here it's really parsing these different language elements. And then in the grounding stage, we actually execute, for example, find the relevant spatial temporal areas or focus the tool use to see where there's most information present. And then the last stage is the event reasoning. So we actually execute the detected ground truth information, we retrieve them from the external memory, and then we put it together, combine the API calls with a reasoning module. And basically this channel, the highlights are that this approach is multi-stage. The comparison leads to more focused, generalized programs. So basically we can adapt the program on the fly. We can see if something else needs to be extracted. And then the program in later stages are informed by the prior stages. So it's a much more flexible framework than if you generate these programs. And so basically what you can also do, this is not something we're doing here, but what is ongoing work, we can actually call these modules directly from the LLM. And then if you look at the experimental results, so here what we have is we have different data sets, NextQA, IBQA, EcoSchema, ActivityNet QA. So basically the last two are long videos and the IBQA and EcoSchema are open-ended questions. So there we have to just produce the question. It's not multiple choice. And then basically the results, if you look at them, random would be just you select randomly an answer. If it's multiple choice and there are 5 answers, then it's 20%. And if there's just an open-ended question, so in IBQA, then it's 0%. Performance of random is 0%. Then the next row shows language only. So this shows that some of the data sets are actually quite biased towards language. Then we give results for ViperGPT. We also implemented ViperGPT++, which is like using exactly the same baselines. And then the next row shows our simple baseline where we just caption every frame and then use an LLM for reasoning. You can see that this actually improves. And then if we add our tool use, we get a further improvement over the simple reasoning baseline. And so we see that there is some gains, but basically you could say for all this additional tool use, the gains are not that big. So what are the factors which hamper our progress? So what we found is that basically many of the localization and spatial temporal localization approaches are still not significantly good to localize the events very precisely. So I think this is something which I talked about this morning. If you want to do temporal localization, there's still progress to be made. So basically the tools, if they're not that good, basically you don't get significant boost in performance. So I think the tools need to be made better. And then obviously another problem here is the data sets. So the data sets here are still quite short. And so basically what you really need to show the power of this, you would need longer data sets. And so basically we're now also concurrently working on bringing out longer video understanding data sets where really this information really matters. So basically you have to be sure that data sets are not saturated or the question is not relevant to these reasoning approaches. And so here, if you look at the different components, so the event parsing, the grounding, and the reasoning, on the top row, we can see that the results with any of these approaches. Then by adding the event parsing, we can see that there's an increase in performance, by grounding another increase, and then the most increase we get by the reasoning module. So the reasoning model puts all the information together and really teases out the relevant information. And then if you compare the state of the art, we can see here that our approach that was actually last year outperformed the state of the art. If you look at results this year, you can see that there's still even further performance improvement. And some of the improvements this year due to larger models. But then I think the component of reasoning is something which can be always combined with stronger models, right? So it's something which doesn't go away. And then if you take an example, so here's the input video of a cat. Why is the cat lying on its back at the end of the video? So if you just use simple baseline with the captioning, we can see that basically it's predicting the cat is tired. And if you look at what's the case here, it just outputs that the cat is lying at the end of the video is lying on the bed. So it's actually thinking that if it looks just at this caption, the reasoning model thinks that it's just tired, okay? So this is actually, the captioning is somehow misleading and it impacts the final prediction. If you look at what the visual programming does, again, it doesn't ask the right question at the right time. So it actually looks at a different instance in the video and again, gets the wrong answer. Basically, the cat is lying and sleeping. So because it looks at the beginning of the video where the cat is actually not playing. And then if you look at our model, what we do here is basically we have first the event question detector. So why is the cat lying at the back? What is happening at the end of the video? Then we ground the cat and we go to the end of the video, we store this information in memory, and then we go to the reasoning model. And then here, actually, we're asking what is the cat doing in frame 42, and you say, then we kind of detect it's playing. You can also ask who are the other people present. There's a person present, and then basically you can, given this information, we can really reason that the person is playing with the cat, and then we obtain the correct answer, playing. And so here, what we can also do, we can also use this to localize the answer in the correct chunk of the video. So you can see here also for this localization task, we outperform the state of the art. And so basically we have seen that this multi-stage reasoning really improves the performance. And this is something we're currently also looking at by looking at more complicated reasoning traces. And these reasoning traces, you can actually combine them with the reasoning modules to really check what's happening in the video and get some informed information of what are the relevant parts in the video and how you can access them and verify them. And so what's actually nice about these reasoning models is that it goes away from these black box models, and you can really understand which are the components that contribute to your process, and you can verify them. So right, you can verify them on a bunch of different data sets. And then one thing, which is obviously we need better data sets. Okay, so and then the second part of my talk, I'll look now how these approaches, this tool use can be used for video generation. So it's a completely different set of approaches, but basically what you want to do here is to synthesize 3D scenes. And the starting point for this work was that basically if you want to synthesize 3D scenes, it's actually nice if you have a concrete 3D representation and not just generate the video. And we'll show that these two approaches can be combined. And so here, what's actually nice is if you look at the Sintel movie, this is like one of the examples where actually the movie is generated by Blender code. So you have Blender code, and this allows you to generate this full movie. So you generate the 3D, the texture, the rigging, layout, animation, rendering, and then from there on, you can really produce a 3D movie. We took this idea as a starting point to actually go from text description to Blender code and then generate an image or video. And so you take a text description as input, and as output, you want to generate the Blender code, which then generates you the scene. And then once you have this, then you can even inject it into a video generation model and then output a realistic video. Okay, and so what is the approach for the SceneCraft work? So first you have the query. So for the query would be, for example, a text, a girl hunter walking in the slum village with fantasy creatures. You give this to an LM. The LM first checks what are the relevant assets which we need to compose the scene. For example, here finds the girl, then determines what are the elements, structured scene elements which we need, and then introduces the relations between the different scene structures and the element in the scene. So then we get this scene graph, which actually gives us the relations between the different objects in the scene and the outline of the scene. Okay. This is important because basically if you don't have the spatial relations between the object, they can be placed in anywhere in the scene. And then the next step is we have a spatial skill library where we have pre-defined some of the spatial relations. And then the final fourth step, which is the important step, is actually that you then generate Blender code. So the LM can be really used to generate this Blender code. And so then what comes in as a tool use, the next step we do is actually use the Blender code to render the scene. So we get the scene rendered, and then we use an LM to check if actually the generated scene corresponds to the text. And so this is actually nice because now we can really use this LM as an agent to check if the scene corresponds to the text, and then can use this to review the code. So then we can say, this is the code. If it doesn't correspond exactly, we want to revise the code, right? So you can see then we can do this over multiple iterations, and we can show that over iterations, the corresponding scene gets closer to the requested prompt. And so here we can see an example for this refinement loop. You can see here, basically you want to have all the people and the alignment in the scene. And after the refinement, it improves. So you can see here the steps after refinement. So basically here we want to have all these people moving around the street and being aligned. And you can see after the steps of the refinement, this is actually happening. And then basically here, This is the inner loop where we have the refinement. So we have the Blender code, which is generated. Then we generate the scene. We verify how closely it's fitting to the generated scene. And then we can actually generate the Blender code. And then we also have the outer loop where we store actually the learned relations, the learned spatial relations. We update them and then know actually once we have generated the scenes, how these relations correspond and can generate them in the memory. So this is where the memory comes in. We have this memory where we store over time all the relations we have seen so far. And then here we have the evaluation. So we compare here. It's like Blender GPT. Blender GPT would be just like a simple existing approach, which takes input the sentence and outputs Blender code. So no refinement, no retrieval, no verification. And we can see here that our approach significantly outperforms Blender GPT. And if you look, what are the scores? The first is clip similarity. So we take the generated scene and compare the text and the scene with the clip score. So you can see that improvement is significant. And then we also have a constraint score. So there we actually we have a small data set which we constructed ourselves, where we have the text, we know what are the relations, and then we actually measure if the objects which are placed in the scene correspond to the constraints. And you can see here that by having our spatial constraints in the loop and our spatial memory, we can really see that our approach verifies the constraints much better. While if you just have Blender code generated without taking into account the constraints, it works not as well. And then if you compare so we had these different ingredients of our approach. We have this learned library of spatial skills. If we remove it, we can see that the performance drops a bit. And then here we can see the constraint scores drops, also the clip similarity score drops. Then if you remove the inner refinement loop, you can see that this results in a very significant drop because we don't have any of this verification anymore. And then we can also see that the scene graph, the relation graph, which is stored and produced during the generation, also adds something to the performance. So all of our different components really help improve the performance. And you can see basically at the end what we get. If we remove all these additional components, we're like more or less up to the performance of Blender GPT. So we can really show by adding this, we can really generate much better Blender code. And then here, a few examples. So here you have 3 trees in a row besides the neighborhood. So you can see that the trees are nicely aligned. You have a new solar system with planets orbiting around the sun. So you can see here again, they're orbiting. And then the last example is actually quite nice. A raccoon is lying on a bed listening to the music. So you can really see that the raccoon is lying there and it has headphones on its ears. And then if we compare SceneCraft and Blender code, you can see on the top the Blender GPT, so the left Blender GPT, SceneCraft right, and you can see 3 different boxes of different sizes stacked on top of each other. So you can see SceneCraft really stacks the boxes because it has these relations, while Blender GPT just has three boxes lying around. And then similarly, this new solar system with planets orbiting around a small star. Again, you can see here the relations of orbiting are nicely respected, while this is not the case of Blender GPT. And maybe then the last example for the trees, you can see that the trees in a row in a neighborhood, you can see that SceneCraft really aligns the trees in a row, while Blender GPT, they're just randomly distributed. And so then the last thing which we did was we used these generated scenes to actually control video generation. So here, this was actually the initial idea. If you have video generation, the scene structure is not really fully controlled. And so basically now, if we use this generated scene as fine-grained control for video generation, what you can see here. So here we evaluate this approach on the Sintel data set. So the Sintel movies come in with a training and a test split. And so basically you can see on the top, we have the first row is just like, it's video generation approach. Here you can see that the clip score and the FED score are very high. So this is without fine tuning. Then if we fine tune on the small held out training set of simple movies, we can see that the performance improves. So the clip score goes up and FVD goes down quite significantly. And then the last two rows, what they do is here, we generate this 3D scene with Blender GPT, and we inject it in the generation. You can see the performance is comparable with the fine-tuned version, but then if we use our SceneCraft scene as an input, as an additional input to the video generation, you can see that the FED score goes down significantly. And then here, again, the scores which we have seen before, the layout and the clip similarity just for the 3D generated scenes. And then if you look at a few examples, you can see here, you have the generated 3D scene, and then you can use it to animate the video. It works well. Obviously, there could be future improvements by really also having these constraints on the 3D objects, which we don't have. We don't have it on the dynamics yet. Another example, this dragon flies over this slum town. You can see that the slum town is nicely assembled. And then last example, a girl hunter walks into the town with fire by the dragon, and you can see that the town is assembled correctly, and the girl is walking and the dragon is lying on top of this. Okay, so we have seen here that the state-of-the-art multimodal LLMs can serve as a strong reward model for self-refinement, but this is an idea which comes over and over again as a critic. So we're currently also using as implementing LLMs as critics for robotics. For example, you can really train a model, either use the model as is to give the reward, but you can also then say you want to fine-tune it for this task. So that's what we're doing in robotics. So you can really use this critic to detect failure cases. And you can use the LLM to generate code with non-parametric skills. And you can then use different tools and functions to help solve the target. So you can access to this library of objects. You can access to this library of spatial skills to further improve the performance. We can really see here that it's not just the LLM by itself, but you really have all these calls to different functions which can really improve the performance. And then you can use this 3D scene generation to guide video generation. So this is something which is nice. And then future work is actually, you can use video understanding to learn a story. So you could imagine you take the first part of something similar to learn a story. And then basically once you have the story, you can use this to generate a new video, or you can learn like different story concepts and use this to animate new videos. So here basically video to generate script, then go to the 3D scene and then back to the video. So this could be like also loop to further improve and in the end verify the performance of your approach. Okay, before I thank you for your attention, and before I conclude the talk, I would just like to announce that we have recently obtained a new internship position in our Google lab in Grenoble. And then if you're interested, please send applications to this email address. Okay, thank you.
In case if you have questions, please come on to the microphone in the middle of the.
On stage vision example you showed, you explained what the decision steps were. How did you come up with those specifics? Just intuition? Have you tried other decision steps?
You mean the 3 steps? How do we, yeah, I mean it was for now it was
Sorry.
The question was, how did we come up with these 3 different reasoning steps? And so was it intuition or did we check out different steps? So yes, obviously when we started working on this, we did try different ways of composing them. But then in the end, I think it's kind of, I mean, I don't have any numbers from comparing different steps. And I think this is also probably not the final answer, right? So basically what we do here is this event extraction first, and then the tool use, and then the reasoning. And what I would do today, so currently what we're looking into is like to have it like more integrated, right? So now you have these approaches which generate reasoning traces. So there's something we're currently working on, which generate reasoning traces, and then maybe while the LLM is executing the reasoning traces, you could then call the tools, right? So you could actually make it more sophisticated and not have it like broken down in this completely separate steps, but have maybe something which is slightly more integrated, right? Which is also the case in the second part where we have the reasoning more integrated in the LMs. I think this would be the final answer, that somehow you can really make the decision on the fly, and then it's even more modular, right? Because like right now we're still like a bit constrained by these 3 steps. I think it's the first nice step, but I think I would go in the future, I would go further and really have this whole thing generated by an LM.
Any other questions? Let's thank Cordelia again.